Right now, somewhere beneath the world's oceans, nuclear submarines are on patrol. They carry enough firepower to end civilizations, and most of the people on the surface have no idea where they are, because that's the point. So today, I'm counting down 15 facts about nuclear submarines that show just how extraordinary and how quietly terrifying these machines really are. Number 15. They make their own oxygen from seawater. A nuclear submarine can stay submerged for months at a time without surfacing. Not days, months. And one of the most fundamental reasons it can do this is that it doesn't need to come up for air, because it makes its own. The process is called electrolysis. Seawater is pumped into a system called an electrolyzer, which runs an electrical current through the water and splits it into its component elements, hydrogen and oxygen. The oxygen gets fed into the boat's atmosphere. The hydrogen gets vented overboard. The system runs continuously, around the clock, producing breathable air for a crew of somewhere between 130 and 155 people. There's a backup system too. Oxygen candles, solid chemical cartridges made from sodium chlorate, can be burned to release oxygen in an emergency. They're slow, they're hot, and they're a last resort. But they exist because redundancy on a submarine isn't a preference, it's a survival principle. The carbon dioxide problem gets solved separately. Scrubbers, chemical systems using monoethanolamine or lithium hydroxide pull CO2 out of the recycled air before it builds to dangerous levels. The atmosphere inside a submarine is actively managed, constantly monitored, chemically maintained. It's closer to a life support system than a ventilation system. But yeah, the electrolysis setup is what makes extended patrols possible. The reactor generates the electricity. The electricity splits the water. The oxygen keeps the crew alive. It's a closed loop that runs off the ocean itself. The only thing the sub needs from the surface world is groceries, which is its own remarkable fact, that a vessel carrying over 100 people running on nuclear power, manufacturing its own air from seawater, is ultimately limited not by fuel or oxygen or mechanical endurance, but by how much food it can carry when it leaves port. The record for the longest submerged patrol by a nuclear submarine is held by HMS Warspite, a British Royal Navy vessel that stayed submerged for 111 days in the 1970s. 111 days underwater, breathing air made from the sea. The hull never broke the surface, the crew never saw sunlight, and the oxygen never ran out. 14. The reactor that runs for decades without refueling. Most warships burn through fuel constantly. Destroyers, frigates, conventional submarines, they all need to return to port or meet a supply ship to keep moving. A nuclear submarine doesn't. The reactor at its core runs on enriched uranium, and a single fuel load lasts somewhere between 20 and 30 years, depending on the class of vessel and how hard it's driven. To put that in scale, a Virginia-class submarine commissioned today will likely be decommissioned before it ever needs new fuel rods. The reactor outlasts careers. It outlasts most of the strategic alliances the boat was built to serve. The reactor itself is a pressurized water design. Enriched uranium fuel heats water in a sealed primary loop to temperatures well above boiling, but the pressure keeps it liquid. That superheated water transfers its heat to a secondary loop, which produces steam, which drives the turbines, which turn the propeller and generate electricity for every system on the boat. The oxygen generators, the navigation systems, the weapons, the lighting, the food prep, all of it runs off the same reactor. And the reactor runs continuously. It doesn't cycle off at night. It doesn't idle in port the way a diesel engine might. It just runs, day after day, month after month, generating roughly 30,000 shaft horsepower in a Virginia-class boat, enough to push 7,000 tons of steel through the water at speeds above 25 knots when needed. There is no exhaust, no smoke, no thermal plume visible from the surface. The energy output is enormous, and almost none of it announces itself to the outside world. But yeah, the real operational consequence of all this is simple. A nuclear submarine's endurance at sea is not limited by fuel. It's not limited by power. It's limited by food. and by the psychological endurance of the crew. The machine could, in theory, keep running long after the humans inside it could yet. The US Navy's nuclear submarines have logged millions of miles of submerged operation across decades of continuous deterrent patrols. The reactor design used in the Ohio-class boats, the ones carrying America's submarine-launched ballistic missiles, was specifically engineered for a lifespan matching the vessel's full service life of roughly 42 years. One fuel load, one boat, 42 years. The reactor doesn't ask much. It doesn't need air, doesn't need sunlight, doesn't care how deep the boat goes or how long it's been under. It just converts uranium into heat, heat into steam, steam into motion, and motion into the quiet, persistent presence of a vessel that can be anywhere and is impossible to find. At number 13, the food is better than you'd expect. There's a standing rule in submarine service, informal but widely understood. The food on a nuclear submarine is the best food in the military, not marginally better, noticeably, deliberately, institutionally better. And the reason isn't generosity, it's operational necessity. Think about what a submarine crew is dealing with. No sunlight for months at a time, no fresh air, no contact with family beyond occasional, heavily restricted messages. The environment is steel and fluorescent light and the constant low hum of machinery. Every sensory reference to the outside world is gone. In that context, a meal isn't just nutrition. It's one of the only things that still feels normal. The US Navy recognized this early. Submarine pay has historically included a separate food allowance above what surface sailors receive, and submarine cooks, officially called culinary specialists, are trained specifically for the demands of feeding a crew of over 100 people in a space the size of a narrow apartment building. 3 meals a day, 7 days a week, for the duration of a patrol that can stretch to 3 or 4 months. The galleys on modern nuclear submarines are compact but fully equipped. Ovens, grills, deep fryers, refrigeration. The menus rotate to prevent monotony. Steak is served regularly, not as a special occasion, but as a scheduled part of the rotation. Lobster has appeared on the menus of US submarine galleys, particularly on holidays. This isn't mythology. It's documented Navy practice. Fresh food runs out first. Fruit and vegetables are gone within the first 2 or 3 weeks of a patrol, replaced by frozen and canned stores. But the quality of preparation stays consistent. The cook's job doesn't get easier as the patrol goes on. If anything, it gets harder, because the crew's morale is increasingly dependent on it. But yeah, the math here is straightforward. 130 people sealed inside a metal tube, carrying nuclear weapons, operating in complete isolation. You can engineer the oxygen supply and the navigation system and the reactor cooling loop. What you can't engineer is psychological endurance. That part you manage with small things, routine, structure, and 3 hot meals a day that someone actually put effort into. When everything else about your environment is steel, recycled air, and the knowledge that there's several hundred feet of ocean above your head, a well-cooked meal is not a luxury. It's a lifeline. The record for longest submerged patrol means the cook never got a day off either. 12. Silence is the weapon. The single most important tactical characteristic of a nuclear submarine is not its speed, its depth capability, or even its weapons. It's silence. A submarine that can be heard can be found. A submarine that can be found can be killed. Everything else, the reactor, the missiles, the navigation systems, is secondary to the boat's ability to disappear into the acoustic environment of the ocean. This is not a simple engineering problem. The ocean is not quiet. It's full of biological noise, thermal layers, pressure gradients, and the sound of other vessels. A submarine has to be quieter than all of it, consistently, across months of continuous operation. The hull of a modern nuclear submarine is coated in anechoic tiles, rubber panels, typically a few inches thick, bonded to the exterior steel. Their job is to absorb incoming sonar pulses rather than reflecting them back to the source. A sonar ping that hits bare steel bounces back clearly. One that hits anechoic tiling gets absorbed, scattered, deadened. The return signal is weaker, smeared, harder to interpret, but the tiles are only part of it. The machinery inside the hull, pumps, turbines, generators, the reactor coolant systems, all of it produces vibration, and vibration travels through steel into water and becomes sound. So, the major mechanical systems on a nuclear submarine are mounted on what engineers call rafts, isolated platforms suspended on shock-absorbing mounts that decouple the machinery from the hull. The vibration stays on the raft. It doesn't reach the steel. It doesn't reach the water. Propeller design matters too. Early submarine propellers created cavitation, tiny bubbles collapsing around the blades, which is extraordinarily loud. Modern submarine propellers are large diameter, slow turning, precision machined to minimize cavitation across a wide range of speeds and depths. The exact blade geometries are classified. The US Navy has prosecuted cases of people attempting to obtain or sell submarine propeller specifications to foreign governments. Crews are trained to move quietly. Tools are rubber-coated. Dropped equipment is a serious incident. During certain operations, machinery that isn't essential gets shut down. The boat gets quieter by subtraction. The USS Seawolf, commissioned in 1997, was specifically designed to be the quietest attack submarine ever built, quieter at its normal operating speed than a Los Angeles-class boat sitting still at the pier. The program cost roughly $3 billion per vessel. So what does all of this buy? It buys invisibility. A submarine that nobody can hear is a submarine that nobody can track, and a submarine that nobody can track is, for all practical purposes, not there. The hull is the sub. If the hull fails, nothing else matters. But if the acoustic signature fails, if the boat makes noise it shouldn't, the mission is over before it starts. 11. Navigation without a signal from anywhere. GPS does not work underwater. Radio waves at standard frequencies can't penetrate seawater more than a few inches, which means the moment a nuclear submarine dives, it loses access to every positioning system that surface vessels and aircraft take for granted. It's on its own, and it still has to know exactly where it is, within meters, after weeks or months of continuous submerged movement. The solution is inertial navigation. There's a system on board called an Inertial Navigation System, or INS, which tracks the boat's position by measuring every acceleration and change in direction from a known starting point. When the submarine leaves port, the system is initialized with a precise GPS fix. After that, it measures motion, every turn, every speed change, every subtle shift in course, and integrates those measurements continuously to calculate a running position. The physics are straightforward. The engineering is not. Inertial navigation accumulates error over time. Every tiny measurement in precision compounds. After days of continuous operation, the drift can become significant, which is why the systems used in nuclear submarines use ring laser gyroscopes and accelerometers precise enough to detect the rotation of the Earth itself. The instruments are that sensitive. They have to be. Modern submarine INS units can maintain positional accuracy to within a few hundred feet after weeks of submerged operation, across thousands of miles of ocean, with no external reference, no satellite signal, no landmarks. To put that in context, navigating from the eastern seaboard of the United States to the coast of Europe and arriving within the length of a city block, using nothing but a record of your own movement. But yeah, there's still drift. So submarines use additional techniques to check and correct their position when possible. They can take fixes from very low frequency radio signals that penetrate shallow water. They can use terrain-referenced navigation, essentially matching the contour of the ocean floor against stored charts. They can briefly approach periscope depth to get a GPS lock without fully surfacing, exposing only the antenna mast for seconds at a time. The charts themselves are a separate problem. The ocean floor is not uniformly mapped. There are regions where the bathymetric data is decades old or simply incomplete. A submarine navigating through those areas is working with uncertainty on two axes simultaneously, where it is and what's below it. And then there's the tactical dimension. Precise navigation isn't just about getting from one place to another. A A submarine-launched ballistic missile needs to know its exact launch position to calculate an accurate trajectory to a target thousands of miles away. The navigation system isn't just keeping the boat safe. It's part of the weapons system. Position is everything. The boat knows where it is because it has been counting every inch of movement since the moment it left. 10. Once submerged, they're almost completely cut off. One of the most counterintuitive facts about nuclear submarines is that the moment they dive, they lose the ability to communicate with the outside world in any meaningful way. Not reduced communication, near total communication blackout. A vessel carrying over 100 people and enough firepower to devastate a continent can receive only the most basic signals and cannot transmit at all without compromising its position. The physics are the problem. Radio waves at normal frequencies, the kind used for standard military and civilian communication, penetrate seawater only a few inches before being absorbed. To reach a submarine at operational depth, you need extremely low-frequency radio waves, known as ELF. These waves have wavelengths measured in thousands of kilometers, and they can penetrate seawater to depths of several hundred feet. The transmitters required to generate ELF signals are enormous. The US Navy operated a facility called Project Sanguine, later scaled down to a system called Seafarer, in the Upper Peninsula of Michigan. The antenna array was buried underground and stretched across tens of square miles of terrain. The Soviet Navy operated a comparable system. These weren't radio towers. They were landscape-scale electrical installations built for the sole purpose of reaching submarines that couldn't be reached any other way. And what could you send through them? Not voice, not data packages, not operational orders with any complexity. ELF transmission rates are so slow, measured in fractions of a character per second, that a message of a few characters could take many minutes to transmit. The practical use was a bell ringer, a brief coded signal telling the submarine to come to periscope depth to receive a longer message through a less penetrating but faster frequency. ELF didn't carry the message. It carried the instruction to go get the message. So the submarine rises to a shallower depth, extends a communications mast for seconds or minutes, receives a burst transmission, then dives again. The whole sequence is a carefully managed exposure, a brief moment of contact with the surface world, then back into silence. But yeah, here's the asymmetry that matters. The submarine can receive. It cannot reply. Sending a transmission from depth would require power and antenna configurations that would immediately reveal its position. So the boat listens. It doesn't answer. Shore-based command can reach the submarine, but the submarine cannot reach back without surfacing or coming close enough to do so. If you're enjoying the video, drop a like and a comment. It really does help the channel out. This one-way architecture is deliberate. A submarine that transmits is a submarine that can be found. The silence isn't a limitation they're trying to overcome. It's a feature they're protecting. The sub listens. The ocean listens back. Neither gives anything away. 9. Depth limits and what happens when they're exceeded. Pressure is the fundamental physics problem of submarine operation. Every 33 feet of depth adds roughly 1 atmosphere of pressure, 14.7 psi, to the exterior of the hull. At 300 feet, the pressure outside the submarine is approximately 10 times what it is at the surface. At 1,000 feet, it's over 30 atmospheres. The hull is holding back a force that, if it found a single point of failure, would resolve itself in milliseconds. The operating depth of nuclear submarines is classified. What navies publish is the test depth, the maximum depth verified in testing, and even that number is often withheld or understated for operational security. What's known publicly is that Los Angeles-class submarines have a test depth in the range of 950 feet, and that crush depth, the point at which the hull fails catastrophically, is estimated at roughly 1.5 times that. Beyond that, the water pressure exceeds what the steel can sustain, and the hull collapses inward faster than any emergency response is possible. A defect in a submarine at 1,000 feet down is not a leak. It's an event, an unsurvivable event. The hull itself is the engineering achievement that makes everything else possible. Nuclear submarines are built from high-yield steel alloys. HY-80 and HY-100 in U.S. Navy vessels, designations that refer to the steel's yield strength in thousands of pounds per square inch. HY-100 steel can withstand 100,000 pounds per square inch of stress before permanent deformation. The plates are welded with tolerances measured in fractions of an inch, then subjected to extensive non-destructive testing, ultrasonic scanning, X-ray inspection, pressure testing, before the boat ever enters the water. The cylindrical shape of the pressure hull is not aesthetic. A cylinder distributes external pressure evenly around its circumference, avoiding the stress concentrations that would form at corners or flat surfaces. Every penetration through the hull, for pipes, cables, torpedo tubes, the propeller shaft, is a potential failure point, engineered and re-engineered to maintain integrity under the full range of operating pressures. And then there are the ballast tanks, which sit outside the pressure hull. They flood with seawater to dive and are blown clear with compressed air to surface. They're not pressure vessels. They're open to the sea at the bottom. The pressure hull is what separates the crew from the ocean. The ballast tanks are just weight management. So what does the destination look like at operational depth? Nothing. Complete darkness outside. No ambient light penetrates to the depths where nuclear submarines operate. The ocean at those depths is black, cold, roughly 2 degrees Celsius in deep water, and utterly featureless to any optical sensor. The submarine navigates entirely by instruments. The crew never sees where they are. The hull is the sub. If the hull fails, nothing else matters. 8. Fire underwater, the emergency with no exit. There's no scenario aboard a submarine more feared by crews than fire. Not flooding, not mechanical failure, not a weapons malfunction. Fire. Because a submarine on fire is a sealed metal container filling with smoke, in an oxygen-enriched atmosphere, at a depth where no outside help can reach it, with nowhere for the crew to go. The oxygen-enriched environment is part of what makes it so dangerous. The atmosphere inside a submarine is actively managed to stay within a breathable range, but that same oxygen content that keeps the crew alive accelerates combustion dramatically. A fire that might be controllable on the surface becomes something else entirely in a sealed pressure vessel several hundred feet underwater. The history here is not abstract. The Soviet submarine K-19 suffered a reactor coolant failure in 1961. Not a fire, but a thermal emergency that required crew members to enter the reactor compartment without adequate protection to prevent a meltdown. Several died from radiation exposure in the weeks that followed. The boat became known among Soviet submariners as Hiroshima. Then, in 1967, K-19 suffered a fire that killed 28 crew members. The same vessel. 2 catastrophic emergencies in 6 years. The USS Guitaro sank at the pier in 1969 during construction. Not a fire, but the broader point stands. Submarines are unforgiving of errors, and the consequences of failure are measured in lives, not incidents. Fire drills on nuclear submarines run weekly. The crew is divided into damage control teams, each trained for specific emergency scenarios. They practice donning emergency breathing equipment, EABs or emergency air breathers, which provide roughly 15 minutes of breathable air from a self-contained canister. 15 minutes to find the fire, fight it, and survive the smoke. The firefighting equipment itself is constrained by the environment. You can't use water freely. Electrical systems are everywhere, and flooding a compartment creates its own emergency. CO2 suppression systems exist for specific spaces, particularly the machinery rooms and reactor compartment. Portable extinguishers handle smaller fires. For anything serious, the damage control teams go in with hoses and EABs and work the problem manually. And then there's the smoke. Even a controlled fire in a sealed submarine produces smoke that fills passageways, reduces visibility to near zero, and makes navigation through the boat, which is already a narrow, equipment-dense environment, extremely difficult. Crew members train to move through the boat by feel and memory, because there will be conditions where they can't see. What's at the end of all this preparation is a simple operational reality. The crew is the only fire department. There's no calling for backup, no evacuation route to the surface, no waiting for help to arrive. The drill ends. The crew stands down. and the boat keeps moving through the dark water, carrying the knowledge that the next drill might not be a drill. 7. Lost submarines, boats that never came back. Between the end of World War II and the close of the Cold War, multiple nuclear and conventional submarines were lost at sea by the world's major naval powers. Some were found eventually, some were not. The ones that weren't found are still down there, on the ocean floor, at depths that make recovery impossible with any technology that has existed or currently exists. The USS Scorpion is the most documented American case. She was a skipjack-class nuclear attack submarine commissioned in 1960, lost in May of 1968 somewhere in the Atlantic Ocean. 99 men aboard. No distress signal received. No mayday. The Navy listed her as overdue on May 27th, and for months the search found nothing. She was finally located in October of that year, roughly 400 miles southwest of the Azores, at a depth of approximately 11,000 feet, more than 2 miles down. The wreckage was photographed by a deep-sea research vessel. The hull had collapsed. The cause of the sinking was never definitively established, though the Navy's official investigation pointed to a possible torpedo malfunction. The exact sequence of events that killed 99 men in the North Atlantic remains to this day not fully known. The Soviet Navy lost submarines too. K-129, a Golf II class ballistic missile submarine, went down in the Pacific in March of 1968, the same year as Scorpion, with 98 men aboard. The Soviets searched for months and found nothing. The Americans, using their underwater hydrophone network, had actually detected the loss event and located the wreck before the Soviets gave up looking. And then the CIA built a ship to try to recover it. Project Azores, sometimes called Project Jennifer in press reports, was one of the most audacious covert operations of the Cold War. The cover story was that billionaire Howard Hughes was building a deep-sea mining vessel called the Glomar Explorer. The actual purpose was to lift a Soviet submarine from a depth of approximately 16,800 feet using a giant mechanical claw lowered on a 3-mile-long pipe string. The operation took place in the summer of 1974. Part of the submarine was recovered. The full extent of what was retrieved remained classified for decades. But yeah, the operational reality behind both losses is the same. A submarine that goes silent stays silent. There's no emergency beacon that functions at those depths, no black box equivalent that survives hull collapse, no way for the crew to signal their position once the boat is gone. The ocean floor is the final destination, and at 11,000 feet or 16,000 feet, it's permanent. The families of the Scorpion's crew received telegrams. The Soviet families received nothing official for years. The loss was classified: 99 men, 98 men, 2 different oceans, the same year. Both boats are still there. 6, surfacing through Arctic ice. Picture a 7,000-ton steel vessel rising vertically through frozen ocean, its sail punching upward through an ice sheet, emerging into Arctic air like a black monolith rising from a white desert. This is not a theoretical capability. It's a routine operational procedure for nuclear submarines assigned to Arctic patrols, and it's been practiced by both American and Soviet, later Russian, navies since the late 1950s. The physics of it start with the ballast tanks. To surface through ice, the submarine approaches from below, identifies a suitable thin spot or polynya, a natural opening in the ice, using upward-looking sonar, then blows its ballast tanks and rises. The sail, which is the reinforced vertical structure rising from the top of the hull, is built specifically to withstand the impact of breaking through ice up to roughly 3 feet thick. The leading edges are hardened steel. The exterior surfaces are designed to take the load of the ice without transmitting damaging stress to the pressure hull below. The upward-looking sonar is the critical tool. Before any Arctic surfacing, the boat spends time at periscope depth or shallower, scanning the underside of the ice sheet above it. Ice thickness varies enormously across an Arctic ice field. Some sections are 10 or 15 feet thick, others are a few inches. The sonar builds a picture of what's above, and the crew selects the thinnest available section, or waits for a polynya to position itself overhead. USS Skate became the first submarine to surface at the North Pole in March of 1959. She broke through the ice 9 times during that patrol, demonstrating that Arctic surfacing was operationally viable, not just theoretically possible. The Skate was a conventional nuclear submarine, not a ballistic missile boat, but the capability she proved became foundational to Cold War submarine strategy. If you can surface anywhere in the Arctic, you can launch from anywhere in the Arctic. And that's the strategic dimension. The Arctic Ocean sits directly between the United States and Russia. A submarine that can operate under Arctic ice and surface at will has effectively shortened the distance between its launch point and its targets. During the Cold War, both superpowers ran submarine patrols under the Arctic ice cap specifically because the ice provided acoustic cover. It's a noisy environment full of cracking and shifting ice, which degrades sonar performance for anyone trying to track a submarine from above or from another vessel. The crew's experience of an Arctic surfacing is brief and industrial. The boat rises, the sail impacts the ice, the hull shudders with the force of it, and then there's open air above the hatch. Arctic air, cold enough that exposed skin freezes in minutes. The record for the deepest Arctic ice penetration by a surfacing submarine isn't publicly documented. What is documented is that both the US and Russian navies continue Arctic submarine operations today, and that the capability to surface through ice remains a core element of nuclear deterrent patrol planning. The ice doesn't stop them, it hides them. 5. Stalking, the silent pursuit beneath the surface. 2 submarines, same ocean, neither one broadcasting its position. One is following the other, close enough to track its acoustic signature, far enough to stay outside the range where the target might detect the pursuer in return. This is called trailing, and during the Cold War it happened constantly. American submarines following Soviet boats, Soviet submarines following American ones, both sides maintaining deniable proximity to vessels carrying enough nuclear warheads to end cities. The practice dates to the earliest days of nuclear submarine operations. By the 1960s, both the US Navy and the Soviet Navy had developed the doctrine and the technical capability to track and follow opposing submarines across ocean basins. The objective wasn't necessarily to attack, it was to know, to maintain contact, to be in position if the order ever came. Trailing requires extraordinary acoustic discipline from the pursuing submarine. You're trying to hold contact on a vessel that is itself trying to be as quiet as possible, while simultaneously ensuring that your own noise signature stays below the threshold where the target's sonar operators would detect a return. The trailing boat has to match the target's speed changes, depth changes, and course alterations, sometimes for days at a time, without ever closing to a distance that would give itself away. The geometry of it is tense. Too close, and the target hears you. Too far, and you lose contact in the acoustic clutter of the ocean. The optimal trailing distance varies with water conditions, thermal layers, and the relative noise profiles of the two boats. Experienced sonar operators develop an almost intuitive feel for the acoustic environment, the difference between a biologics contact, a distant surface ship, and the faint, structured sound of another submarine's machinery. And then there were the collisions. In February of 1992, the USS Baton Rouge, a Los Angeles-class attack submarine, collided with the Russian submarine Kostroma in the Barents Sea while trailing her at close range. Both boats were damaged. Neither navy officially acknowledged the incident for some time. In March of 1984, the USS Kitty Hawk aircraft carrier collided with a Soviet submarine that surfaced unexpectedly beneath it in the Sea of Japan. These weren't isolated accidents. They were the predictable friction of two nuclear-armed navies playing a permanent game of proximity in the same dark water. What you reach at the end of a successful trail is a kind of tactical intimacy. You know where the other boat is. You know its speed, its depth, its rough heading. You've been living in its acoustic shadow for days. The crew of the target submarine has no idea you're there. That knowledge, the asymmetry of it, is the entire point. A submarine that can trail another submarine undetected has already won the first phase of any conflict that might follow. The Cold War ended. The trailing didn't. 4. The weapons load of a single Ohio-class submarine. There's a vessel in the United States Navy's fleet, several of them actually, that carries more destructive capacity than was used by all combatants combined in World War II. Not comparable to it. More than it. A single Ohio-class ballistic missile submarine carries 24 Trident II D5 missiles. Each missile can carry multiple independently targetable re-entry vehicles, warheads, with a yield in the range of 100 to 475 kilotons each, depending on configuration. The bomb that destroyed Hiroshima had a yield of approximately 15 kilotons. Do the math on a fully loaded Ohio-class boat and you arrive at a number that doesn't fit comfortably in a sentence. The Trident 2D5 itself is a remarkable piece of engineering. It's approximately 44 feet long, roughly 74 inches in diameter, and weighs around 130,000 pounds at launch. It burns solid fuel across 3 stages, reaches altitudes above the atmosphere, and delivers its re-entry vehicles to targets at intercontinental range, up to approximately 7,000 miles, or that with an accuracy measured in a few hundred feet. From launch to impact, the flight time to a target in Europe from a submarine in the North Atlantic is roughly 15 minutes. The submarines that carry them are purpose-built for this single mission. Ohio-class boats are the largest submarines ever operated by the United States Navy. At 560 feet long and displacing approximately 18,700 tons when submerged, they're roughly the length of 1.5 football fields. The missile compartment, the section of the hull containing the 24 launch tubes, occupies the middle third of the boat and is essentially a separate structure within the pressure hull, a cylinder of launch tubes arranged in 2 rows of 12. The tubes themselves are each about 7 feet in diameter and extend through 2 decks. When a Trident missile is launched, it's ejected from the tube by a gas generator, essentially a controlled pressure pulse, and travels upward through the water column before the first stage motor ignites above the surface. The submarine barely moves during a launch. The recoil is managed by the boat systems. You could, in theory, fire multiple missiles in rapid succession without the submarine needing to surface or maneuver significantly. So, what does the destination of all this engineering look like from the inside of the submarine? It looks like a control room. Screens, consoles, officers at stations. The launch sequence is procedural, systematic, governed by authentication codes and physical safeguards. There's no dramatic countdown. There's a checklist. The Ohio-class boats currently on patrol carry the majority of America's deployed nuclear warheads. The exact number of warheads per missile is configurable and classified, but under current arms control frameworks, each submarine deploys no more than a specified number of warheads in total. The number is still enough to end multiple countries, from one boat, sitting somewhere in the ocean right now, where nobody outside the US Navy knows exactly where it is. One submarine, one patrol, enough. 3. The 2-man rule, and why no single person can launch. Locked inside every nuclear submarine that carries ballistic missiles, there is a procedure so deliberately engineered against individual human action that it requires 2 people to execute simultaneously, in physical locations far enough apart that one person cannot reach both stations alone. This is the 2-man rule. And it exists because the people who designed the launch system understood something important. The most dangerous variable in a nuclear weapon system is not a mechanical failure or an enemy attack. It's a single person deciding to act unilaterally. The concept was formalized in the United States nuclear arsenal during the 1960s. As ballistic missile submarines first entered service, the basic structure works like this. To execute a launch, 2 officers, each holding a separate key, must insert those keys into physically separated panels and turn them simultaneously within a defined time window. The panels are positioned far enough apart that one person cannot reach both at the same time. No single individual, regardless of rank, regardless of what orders they claim to have received, can complete the sequence alone. But the 2-man rule is only the final physical gate in a much longer authentication chain. Before any key is turned, the submarine must receive a valid emergency action message, an EAM, from the National Command Authority. The message arrives encrypted, and its authenticity is verified through a series of codes that the crew checks against sealed authentication materials stored aboard the boat. The crew doesn't decide whether the order is legitimate based on their own judgment. They verify it against a cryptographic system designed to be unforgeable. And then there's the question of what happens if an order arrives that the crew believes is illegal, an order to launch that violates the laws of armed conflict or that arrives without proper authentication. The US Navy's position, embedded in its personnel screening and training, is that crew members are expected to refuse an unlawful order. The psychological screening for submarine crews assigned to ballistic missile boats is the most rigorous in the military specifically because of this. The Navy needs people who will follow a valid authenticated order and refuse an invalid one, and who can tell the difference under conditions of extreme stress, isolation, and uncertainty. The physical environment where all of this happens is a control room roughly the size of a large living room, full of consoles, displays, and people at stations. There's no dramatic lighting, no countdown clock on the wall. The launch procedure is documented in binders. Officers work through it methodically, step by step, checking each action against the written procedure. So, what does the destination of this process look like if it's ever completed? 24 missiles leaving the tubes in sequence, each one riding a gas pulse up through the water column. First stage igniting above the surface, the boat continuing on its course below. The crew would know what they'd done. They'd continue their duties. There's no protocol for what comes next because what comes next has never happened. The procedure is not a battle plan. It's an apocalypse plan, designed to be used only once. Designed above all to never be used at all. 2. Second strike capability, the guarantee that ends wars before they start. Most weapons exist to be used. Nuclear submarines exist to make their use unnecessary. The entire strategic logic of the ballistic missile submarine, the reason these vessels were built, the reason they're still on patrol today, the reason both the United States and Russia maintain continuous at-sea deterrent patrols with no gaps, is not what they can do if launched. It's what their continued existence prevents. The concept is called second strike capability. Here's the problem it solves. In the early nuclear age, both superpowers kept their nuclear weapons primarily on land, in missile silos and on bomber bases. This created a dangerous instability. If one side believed the other was about to launch a first strike, they had a powerful incentive to launch first themselves, because a preemptive attack might destroy enough of the opponent's weapons to limit the retaliation. The weapons that were supposed to prevent war were actually creating pressure to start one. Use them, or lose them. That's the logic, and it's terrifying. A nuclear submarine eliminates that logic. A submarine on patrol is hidden. Its location is unknown to anyone outside the chain of command that deployed it. An adversary planning a first strike cannot target what they cannot find. Even if a nuclear attack destroyed every land-based missile, every bomber base, every surface ship, even if it destroyed every city, the submarines at sea would survive, and they would retaliate. This is the second strike, the guaranteed response, the blow that arrives after you've already been hit. And here's the strategic consequence that the Cold War theorists worked out in the 1950s and 60s. If retaliation is guaranteed, there's no scenario in which a first strike is rational. You cannot win a nuclear exchange if the other side has submarines at sea. You can destroy their cities, but you cannot stop the response. The submarines are already out there. They're already aimed. They'll launch from positions nobody knows against targets already programmed into their missiles, and nothing you can do in the first strike will change that. So the submarine doesn't need to fire. It just needs to exist. The knowledge that it's out there, somewhere, unlocatable, armed, and under orders to retaliate, that knowledge is what does the work. It's not a threat that gets made in speeches or diplomatic cables. It's a structural fact of the strategic environment that every nuclear-armed government understands and has understood for decades. You cannot win. Therefore, you don't start. The United States Navy has maintained continuous at-sea deterrent patrols since November of 1960. Not a single day without at least one ballistic missile submarine on patrol. The British Royal Navy has maintained continuous deterrent patrols since June of 1969. These aren't gaps in the record. The continuity is the point. The moment there's a gap, a day, an hour, the deterrent loses its certainty, and certainty is everything. But yeah, The paradox at the center of all this is real, and it's worth sitting with. The most destructive weapons ever deployed by human civilization are kept at constant readiness, manned by trained crews, loaded and aimed, specifically so that they will never be used. The deterrent only works if it's credible. It's only credible if it's real, and it's only real if submarines are out there right now, in the dark, waiting for an order that everyone involved is hoping never comes. The knowledge that a retaliatory strike will come from a platform that survived the initial attack because nobody knew where it was. That knowledge is what keeps the weapons silent. Number 1. The paradox at the bottom of the ocean. Right now, as you watch this, there are nuclear submarines on patrol. Not on standby, not in port, on patrol, moving through deep water, maintaining radio silence, carrying enough warheads to end the functioning of modern civilization as it currently exists. The United States has them out there. Russia has them out there. The United Kingdom, France, China, all of them maintain submarines at sea continuously, with no gaps in the patrol record that would signal vulnerability or hesitation. This has been true, without interruption, for decades. The paradox is this: the weapons that could end the world are the reason the world hasn't ended. Not metaphorically, structurally. The logic of nuclear deterrence, built on the second strike capability that submarines provide, has held imperfectly, nervously, with several near misses that only became public knowledge years after the fact, for over 60 years. The Cuban Missile Crisis of 1962 brought the world closer to nuclear exchange than most people alive today fully appreciate. In October of that year, a Soviet submarine, B-59, was being depth charged by US Navy vessels near Cuba. Cut off from communication with Moscow for days, the crew didn't know whether war had already started. The submarine carried a nuclear torpedo. The decision to use it required agreement from 3 officers. 2 agreed. 1, Vasily Arkhipov, refused. The torpedo was not fired. 1 person. 1 refusal, in a submarine. The architecture of deterrence is built on the assumption that the system will hold, that the authentication procedures will work, that the 2-man rule will function, that the crews will maintain discipline under conditions of extreme isolation and stress, that the submarines will remain undetected and therefore unchallenged. It has held, but it has held with human beings inside it, and human beings are not machines. What's at the center of all this? The destination the entire system is aimed at is not a target. It's a condition. The condition is called strategic stability, a state of affairs in which no nuclear-armed power calculates that a first strike is survivable or rational, because the submarines guarantee retaliation regardless of what the first strike destroys. The submarines are the guarantee. They're the reason the calculation never tips, and so they stay out there. Crews rotate, patrols end, and new ones begin. The boats themselves are refueled once a generation and sail on. The missiles sit in their tubes, armed, targeted, maintained, never fired. The sonar operators listen to the ocean. The navigators track position to within meters across thousands of miles of dark water. The cooks prepare 3 meals a day. The reactor runs. Nobody on the surface knows exactly where they are. That's the point. That's always been the point. The sub doesn't need to fire. It just needs to exist. And somewhere below the surface of the ocean right now, it does. Moving without sound. Carrying the weight of a deterrent that works precisely because it never has to be demonstrated. The world remains intact not because the weapons were never built, but because the submarines that carry them can never be found. They're out there in the silence, and the silence is the strategy. If you thought these facts were sobering, you're not going to believe our video on the most dangerous military operations in history. Click here to watch, and I'll see you over there.